Hi everyone. Let's dive into our first topic, an overview of fracture mechanics. Understanding this concept is crucial for predicting how and when materials might fail due to cracks. Ready? Let's get started. Imagine you have a piece of metal with a small crack in it. Over time, as the metal is used and stressed, that small crack can grow and eventually cause the entire piece to fail. Fracture mechanics helps us understand and predict this process. Before we dive deeper, let me ask you a quick question. What do you think is more dangerous for a material? A small crack or a large crack? Pause for a moment. Well, it might surprise you, but even a small crack can be very dangerous because it can grow under stress. Fracture mechanics is a method we use to predict when a part with an existing crack will fail. It's like being a detective, figuring out how cracks grow and cause problems. A crack increases the stress around it, making the material more likely to fail. This is why even small cracks can be a big deal. Now, let's compare two different approaches to understanding material failure. The first is the traditional strength of materials approach. This method is pretty straightforward. We determine failure based on when the stress applied to a material exceeds its strength, yield strength, or ultimate strength, depending on the failure criteria. Think of it like a rubber band. If you stretch it too much, it will snap once you exceed its limit. In fracture mechanics, we look at something called the stress intensity factor, which considers the applied stress, the size of the crack, and the shape of the part. Failure happens when this stress intensity factor is higher than the material's fracture toughness. And once the stress intensity factor is too high, the crack grows quickly and the part fails. This approach helps us predict and prevent sudden failures. So in the fracture mechanics, there are two terms, the stress plus the shape and size of the crack, while the strength of materials approach only one term is to know failure will occur or not. Now, let's talk about something really important in fracture mechanics. Stress concentrations around cracks. This will help us understand why cracks can cause such big problems in materials. Imagine you have a piece of metal with a crack in it. This crack acts like a stress magnet, pulling in stress and causing it to spike near the tip of the crack. Let's break down why this happens. Have you ever noticed how tearing a piece of paper is easier if you start with a small cut? That's because the cut acts as a stress concentrator, just like our crack in the metal. Here, we have a formula that tells us the theoretical value of stress at the tip of an elliptical crack in an infinite plate. In the formula, sigma is the nominal stress applied to the material. R0 is the radius of curvature of the ellipse at the crack tip. A and B define the size of the ellipse with A being half the length of the major axis and B being half the length of the minor axis. The formula tells us that as the radius of the crack tip, R0, gets smaller, the stress at the crack tip, sigma max, gets much larger. In theory, if R0 approaches zero, the discontinuity became a sharp crack, and the stress would approach infinity. But in real life, materials can't handle infinite stress. Think of it like this. If you press a sharp needle into a piece of rubber, the stress at the point of the needle is very high. If the needle was infinitely sharp, which is not possible, the stress would be infinitely high too. But what actually happens is the rubber deforms around the needle, distributing the stress. This situation where stress theoretically goes to infinity is called a stress singularity. It's not physically possible because materials can't handle infinite stress. Instead, the stress spreads out over the surrounding material, causing plastic deformation, permanent change in shape, some distance away from the crack tip. You can watch the complete course of fracture mechanics and fatigue concepts theory and ABAQUS software implementation on Udemy from the link in the description. Thank you for watching, subscribe for more, and see you next time.